Јоре, добар ден или добра вечер на сите. Ви благодарам што пак во голем број се одзовте на петтиот Data Science Macedonија meetup настан оваа година. Јас сум Горан, еден од организаторите на Data Science Македонија и сакам само на кратко пред да почнеме со презентација да направам еден краток wrap-up на тоа што се случи оваа година.
Just as a reminder, maybe we should speak in
Yes,
English.
Sorry. Do we have confirmation for the link? Okay, this was the first time that I was speaking in Macedonian on these events. So my name is Goran. I'm one of the organizers of the Data Science Macedonia meetup, together with Georgi, Krisitjan, and Valentin. Valentin, he's not here at the moment. So this is our fifth event. We started in May this year, I think. On 55 events, we already have 8 speakers, together with the 2 speakers that we're going to have today. And our goal is to promote data science, artificial intelligence, and machine learning among the community in Macedonia. So I think we had a strong start. Today we are trying something new. For the first time we have an online stream, so everyone who is not able to participate here is able to listen and see what we are doing here online on the link. Together with one of our partners, that's JS Guru company from Banja Luka, Bosnia. They have organized viewing of this event through the stream, and we are going to have questions also from Bosnia at the end of this event. If everything goes fine, maybe we will consider to add more of the meetups to stream them online during the next year. For the next year, we plan to continue with the data science meetup. Approximately, the plan is to have somewhere between 6 to 9 meetups per year, but we are going to discuss about the format. Aleksandar here will present the whole data-driven pipeline that Netcetera is utilizing for several of their projects, and then Krisitjan will share more insight about fraud detection system for healthcare insurance company that was developed for the Middle East, for an insurance company in the Middle East. And to stress something more, this is not a project that is developed completely by Netcetera. They are giving back to the community and they're collaborating with the community. One of the organizers and professor at Finki, Georgi Merjarov, I know that also participated on the project. So it will be really nice to see how that experience went through. At the end, because this is our last meetup before the next year, I would first and foremost like to thank Finki, the Faculty of Computer Science and Engineering, who allowed us to be present here for 4 times in this room for free. So they're kind of our sponsors at the moment. So that was great. And also everyone who volunteered and contributed by bringing new guests, and the company who helped us to organize these events. Happy New Year and happy holidays from us. And now I will leave my place, and Alex.
Yeah, thank you. Thank you everybody for joining as well. I mean, in today's presentation, we just want to show you how was our journey when we started thinking of machine learning projects or introducing machine learning in our projects, and where we are right now. I mean, first, maybe I can just shortly tell you about the company. Netcetera is created in '96. The headquarters is in Zurich in Switzerland. Currently, it is in 6 countries. It has more than 500 employees and 13 cities. I mean, from the countries, we have Switzerland, Germany, Austria, Liechtenstein, Macedonia, and Emirates. We have a range of business domains where we are present. I mean, we are mostly in finance, insurance, and payment services, but we also do a lot of projects and products in transport, healthcare, government, publishing, media, and so forth. And what is characteristic for us is that we don't have one or some very big customers. We have quite a lot of them, which is also, you know, later when I tell you about our opportunities in machine learning, this is something which is very handy, because here among all of these customers we can pick up a lot of different opportunities. So very often when we discuss, we say we are a software development company, but you know, in my mind, we are more working in the problem-solving business. You know, in the past, we always had something like a customer comes to us and says, here are the requirements, here is the specification, build me a software for that. But as the time passes on, the customer only says, I have this problem, I need a solution for the problem. And this is also something that affects our mindset, how we are thinking, how we are solving problems, how we provide all of those solutions. And I also think in the future, I would say quite near future, it will be even furthermore that we would have to go to the customers and tell them, look, this is your problem and this is your solution. Very often for problems that they don't even know that they have them. In order to do that, of course, we need to do a lot of innovation, make some new approaches and, you know, make new kind of solutions. But innovation is very hard. It has been a tagline in the last 20, 30 years. Everybody says, you know, we can do innovation, we are innovative and so forth. We have tried many times and we have also failed many times in this area. So at Netcetera we said, let us start some new platform where we can be very innovative. We called the platform Sparks. And there we said, we just want to increase the innovation throughout the company. We want to make everything to be very easy, to be able for the people to work on new ideas, to engage as many people as possible, also to make everything very transparent. Of course, in the end, to generate new businesses, to make new solutions, as I mentioned before. So how does it work? We always think of a idea as something around which we are all connected when we are talking about innovation. So we have people who have their time, who are investing their time. We have a specific portal where everything is transparent. The whole process is iterative. We always try to refine in iterations on all the ideas. And again, we have a board that is controlling, but it's only very loosely controlling the whole process. So as opposed to companies that have dedicated R&D departments, we say that we do integrated innovation, which means there is no dedicated R&D. We have everybody can innovate throughout the company, and the whole organization is just made in order to enable and facilitate the whole innovation process. In the end, we always focus on the team because the team is the one thing which is the most important whenever we want to make a new product, a new solution. So we try to organize, you know, Sparks lunches where we gather a few people, we go on lunch, we discuss about certain things. We organize internal competitions, hackathons, for example, code camps where we go somewhere for 2-3 days just to work on some problems. We have our own labs like iOS app, Android lab, and so forth. And we also very often organize, we call them powwows. These are idea brainstormings, where we say, okay, this is a topic on which we want to talk about, and then we go and we discuss the topic with various groups of people. We also use quite a lot business model canvas. I mean, this is one very specific thing on how to evaluate an idea and how to kind of prove whether that idea is correct or not correct or whether it can work. So just to go back, the key points, everybody can innovate. It is a community-based effort. Transparent, also collaborative. We have our portal where all the ideas are documented there. Everybody can comment. We also have the social part, you know, with the likes and dislikes on the idea, which is very handy, I would say. Quite often also, when every week we have a Sparkle of the Week, which is a focus on a certain topic. And for us, this is important because the company grew quite a lot, that people from different parts of the company or even different countries can just sign up and work on a certain idea which is in progress at the moment. And our organization is made just to, as I said, enable and facilitate. It is very loosely controlled. We have, this is just to go one back, enough budget. That is very important thing. Because, you know, if we would have had unlimited budgets, things would be very, very easy. And in the end, we have easy to fail culture. This is, again, another key point, because we always say we want to try as many things as we can, there is one quote, I think it was from Edison, I think. He said, before I invented the light bulb, I invented 1,000 ways how not to make a light bulb. So we always have to try. I would say on every 20 ideas that we try, there is one that works for us. I would say the ratio is something like that. And there we said, this is something like 3 years ago, we said we want to really focus our innovation. We created 6 focus topics: blockchain, augmented reality, machine learning, Internet of Things, conversational interfaces, and future payment technologies. I mean, this is just a list of, I would say for somebody, a wishful thinking, but we really created teams for all of those focus topics, and machine learning is one of those. And when we created the focus topics, we said, okay, where is the innovation really coming from when we think about it? It comes from the employees. This is the bottom-up approach. It comes from managers. This is the top-down approach. It can be an external person, conference, or anything. It can be within our projects, or it can come from customers. So then here I would focus more on the machine learning stuff. We made the plan and we said, okay, we are going to do all of these things. So it's build up the know-how, explore the possibilities, just check what can we do. But then came the important part. This is why I also showed you the innovation stuff. We took several teams of people. We just sat down and we said, okay, what are the things that you do in your projects right now, in your daily work? This is what we can do with machine learning after we kind of built up the know-how. This is what we can do. Let us find the match. We sat down with technical people, technical teams. We also sat down with sales and account managers, because usually they also know their customers much more, and they are in a daily contact with the customers. They know what kind of problems that they have, and also they know where we can find some solution for them. After this, we build up some proof of concepts and demos. One very difficult thing for us when we do machine learning projects is to convince the customers actually to prove that what we are doing is really valuable for them. And in order to do that, we always need proof of concepts and demos. And also on the other side, for us, the technical people, this is the interesting part, where we really sit down and do some software. Then we identified the projects, we contacted the customers, and in the latest stage we started creating the projects and the products. So I just took out 6, which I think are kind of more easier either to explain or where we had some better results. First we had the guy who also had a partner company, who actually had the problem of categorizing all the documents. This is kind of a company that does legal stuff. And then they said that they have thousands and thousands of documents from their customers. I would say maybe even hundreds of thousands from their customers, and they very often, they cannot go in all the details of all the documents. First we did categorization of all the documents there, and then for each of the documents we went through the paragraphs and verified whether each document from their own group consists of all the paragraphs. So I would say, for example, we were able to detect if a rental agreement didn't have a termination date. That would be one anomaly that we were detecting in this case. I mean, this project didn't continue, didn't kind of fly off because the customer was not convinced in the end. The next one is fraud detection in payment. I don't know if you know what is 3D Secure. 3D Secure is kind of an augmented security for credit card payments. We have built a software for 3D Secure processing, and we as Netcetera, we are a processor for those transactions. So we have a lot of banks who are our customers whose transactions go through our system, and in many cases, this is a second password which is demanded where a person wants to buy something on a website. And there we realized that we have a lot of data, a lot of transactions which are passing through. We did a prototype. We tried to find out anomalies. I mean, the problem in this for us was that we had all the transactions, but we didn't have any information whether a transaction is fraudulent. because the transactions were going through us. It went to banks. The banks later on would receive an information that a transaction is fraudulent, but they never send that back to us. So, and because of that, we couldn't work in supervised mode. We had to do something in unsupervised, and we only tried some anomaly detections, which in the end did discover something, but that was not enough. This project currently is on hold. We are negotiating with the banks to receive fraudulent information back, and if we are able to do that, then I'm pretty sure that, that it will continue. The third one is medical data. We have one customer in Emirates, which is that is a Ministry of Health, and they're processing all the health insurance claims. So in the whole country, all the claims are going to the ministry, they're processing them and paying back and forth everything which needs to be paid. They also have a lot of medical data about all the people. This is the medical data that comes with the claims. Of course, we went to the customer because it's a huge potential for us. That's a customer that is maybe our customer in the last 8 or 9 years. And in the discussion, they complained that they have a lot of patients with a wrong gender or a wrong place of living and so forth. We did some models. We very easily find the anomalies. I think out of maybe 6 million records, they had 8,000 people with the wrong gender. I mean, some of them were easy. You know, if you have a guy who made a pregnancy test, you immediately know that there is something wrong with the gender of that person. I just want to go a little bit back. I mean, the other 3 cases that you see here, I will shortly talk about the operational cost valuation and phase detection, and then Krisitjan will discuss the fraud detection in health insurance, and that is the bigger part of our today's presentation. We always have a data-centric view. You know, for every problem that we have, it's always first the data itself. Do we need to create the data? Do we gather the data? How do we get it? Once we get the data, then is the processing part. You know, there is the whole cleaning. We need to add semantics and so forth. After we do that, we need to store and persist the data somewhere. In the next step, we have the analysis where we analyze the data, check. We also add some business domain knowledge. And the latest step is the modeling. As I said, one of the bigger problems is how to gather and how to create the data, how to identify what is the information that we have there. But also, you know, all the customers are very, I would say, picky about giving out the data out of their grasp, I would say. So in many of these cases, we actually work with the data directly on the customer side. In some cases, we have our own server that is installed at the customer. They copy the data on the server, and then through remote desktop, we connect and do our analysis and so forth. This also, I mean, this eliminates the risk that the data can go out. Usually it's very sensitive, you know, like the payment or health information. It's I would say, very risky if the data goes out. So, as I said, there are few challenges. You know, the customer awareness, usually it's difficult to convince them that this will bring back some value to them. On the data side, it's always the consistency. You know, we receive many of files, even if they're coming from the same source. There are always different coding systems. Maybe sometimes the records are corrupted, and you know, so forth. Also, the data quality sometimes is numbers, the ranges of numbers, and so forth. And as I said, the quantity of the data is also very important. That more data we have, usually for our algorithms, is much better, and the results are much more correct in those cases. So here I just very quickly outlined that in the processing part we have cleaning, unifying the whole semantic stuff, also connecting all the different sources of data that we receive. In the analysis part, we do a lot of, first we run some anomaly detection algorithms, and then we do a lot of plotting. So we try to plot all the features, you know, all the different things. We also do the dimensionality reduction just to see how the data is scattered. Here in this case, we also add some expert knowledge, like what are the features and what do we get with each of the features. We do a transformation as well. Very often, depending on the distribution, we can do different transformations just to get the nicer distribution in these cases. We also do a lot of feature engineering, where we add additional features from different sources, or in many cases we also do some data calculations and add them as an additional feature. Then comes the modeling, and in the modeling, first we build the model, then we try and evaluate, then we correct some parameters on the model, and then we go to step, this should be go to step 0, as we are developers back on the build part. Once we finish everything, we do the training of the final system, and then we run it in the production. So one of the cases that we had there is a company for which we do software for evaluating properties. The name is Wust Partner. They have a software where their agents go on the field, collect data about different properties, enter the data, and then come up with calculations for the values of the properties. These are not properties like a house or an apartment, but it's a whole building or a whole area which consists of many houses and apartments. And there are quite a few methods that they have. We have built the whole software for them, and it's also, I would say, quite a big team for quite a few years that works on that software. And of course, on our workshops, this was kind of an immediate candidate. We said they are doing all of their calculations. They have some mathematical formulas and so forth for the evaluations of the properties. And we said, why don't we build a model that can actually calculate or that can predict the value of a property? When we went and when we spoke with them, they said, no, this is too big for a first step. Let's just do prediction of the maintenance and running costs of the properties. And this is what the project is about. The maintenance cost is, all the repairing and all the stuff, and they have quite a lot of land, grass, mowing, cleaning, and all the stuff. Of course, for us in Macedonia, this is a little bit strange because our running and maintenance costs are quite low, at least what the buildings are paying. They use hedonic regression, which is based on economic formulas, and this was the scope of our project. In the beginning, as we defined the problem, we got the data because we have a direct access to them. We did the normalization, standardization. This was quite I would say, an interesting process. In the cleaning, we removed the missing data and outliers. Of course, as I said, we did a lot of visualization stuff. And then in the end, we deployed and retrained the solution. So in the beginning, we started with all the traditional stuff. Linear regressions, regression trees, SVMs, with a lot of simple models. In the end, we got the best results with XGBoost. I think XGBoost is something that lately is everybody is going in that direction. Whenever I speak on some conferences or with some other colleagues, they are always getting the best results there. For all of those models, we used cross-validation. I think in the end we finished with the 10-fold cross-validation, even though usually we use the 3-fold in these cases. The deployment of the solution in the end is we have. Do you hear me well? Because okay. So the WUP is the code name for the project, and here we have the backend. And then we have a runtime system where we run the models. On the right side, you can see the training system. So the training system is not online all the time. It just collects the data. We run the training, we verify, and then we publish the model to the runtime system. They have a very specific request that every calculation they do and every prediction they do, they need to be frozen in time. So, for example, in 2018, they use one model for a prediction. In 2019, we will publish a new model, but both of those models need to stay online because they want to redo the calculation for the year with the parameters that we have for that year. And for that case, we need to keep all the models. Here, everything is, in this case, in the production is Dockerized. We have different Docker for every model. There is a proxy that routes depending on the year or the model version which is requested. NCF Faces is as I mentioned, the fifth project on the list. This is a face recognition project, our own internal. We envision it as a product for social events. If we have pictures from people which are attending the social event, then with the camera, a person can just very quickly go, point the camera, I would say real-time live camera, and immediately all the people on the camera would be annotated with their names, abbreviations, and so forth. And this consists of two problems to be solved. One is the face detection stuff, and the other one is face recognition. So for the face recognition, we use Siamese networks where the network is trained by using two parallel identical networks and then a function which is calculating the distance between the output of the embeddings of the two networks. So here, for example, when we use a picture, we feed the picture on the left network and a picture on the right network. We receive embeddings, vectors for those pictures. We calculate the distance, and then we retrain the network based on that distance. Now the point is that here we can have a function which is, returning the calculating the distance and returning the feedback to the network based on the fact whether we use the same picture, similar picture, or whether we use completely different pictures. Maybe a little bit I can explain it maybe a little bit better on this side. We can train the network by using 3 pictures at once. We have the anchor or the referral picture, which is the top one. We have a similar one, the positive, and then we have a completely different one, which is the negative. And then the training function tries to minimize the distance between the anchor and the positive, and to maximize the difference between the anchor and the negative. There is already a trained model, which is called FaceNet, which has been trained with many millions of pictures, which in this case we took it and we used it in our product. So our product works as a web, because we want to test it. It's more easier in that case, or on a mobile. First we do a pre-processing of the image just to see whether the orientation is correct. Also to verify that the size and the resolution and everything is in the ranges. Then we do a face detection. We find the faces on the picture and we send those faces to FaceNet, as I said. We receive back embeddings, vectors for each of the faces, and then based on the distances, we can identify who is the person on the picture. Which is very important in this case. We have all seen face detections, face recognitions, and many other algorithms. Which is very important with this approach is that we can use only one photo per person for the training system. And I can just tell you there was a very interesting situation on one of the seminars where we went this year. There was one of the colleagues, he went to one other colleague, he started discussing, and then he came back to me, he said, I completely, I made an error with this colleague, with the girl. I thought she was completely different person because they look alike so much. And I was like, okay, this is a very nice case for us to check and verify the app. So I called them, and then I made the photo. One of the abbreviations is not visible, but this is absolutely correct. You can see that both of them are quite similar. I mean, for us, for human eye, but for the algorithm, it just works perfectly. And those below are the two photos with which we have trained the system. For us, maybe this whole application is not that we have did something completely new, but we have used some very nice and very new approach in this case. And our future plans with this product is to make it a product, offer it to our customers. There are already customers that are very interested in this one, not on the social event organizing, but in a company, especially in a bank, just to recognize the people who are there. Just very shortly from my side, where we now plan to continue is the fraud detection in credit card payment. As I said, we are waiting from the banks. We also have a model on environment data predictions. These are time predictions, especially for the pollution. I don't know if you know about pulse.eco. Okay, I'm pretty sure you know about Skopje pulse.mk. Pulse.eco is the newest one that we did, which actually covers several cities in Macedonia. I think Bitola, Tetovo, Kičevo, and some others, Ohrid. We have sensors there as well. We collect all the data about the pollution from the sensors, and now we are modeling just to verify and see how the pollution is growing at what time and how it is also propagating. For the property valuations, we want to do the next big thing to value the real property values, and we also plan to do a model for Macedonian language for speech recognition. Don't know if you know jargon.mk. This is based on Mozilla Common Voice, where everybody can just go and donate their voice for the speech recognition movement. There are a lot of sentences, and everybody can just go, press record, read the sentence, and then we can use that data in order to train the system. I will pass over now to Krisitjan. He will explain the last project on the list.
Thank you, Alex. Test. Ne? Ne?
Yeah.
Test. Test. Check. Test. Okay. Hello everyone, I'm Krisitjan, and today I'll present to you about a product that we'll be developing at Netcetera for the past 3 years. Its origins are the first Sparkle projects that Alex mentioned to you. So this project arrived from a Spark innovation topic, and it's about detecting fraud, waste and abuse in the medical claims that are present in the healthcare sector in the Middle East. The product is meant to help the insurance providers fight this WOF, because as a side effect it increases the insurance premiums of the members themselves. So we need to find a way to control the waste, abuse and fraud and limit it as much as possible. The core team behind this project is, of course, myself, Kirill Milev, who is the product owner, Georgi, who is the consultant, Alex, and Spase, who is the technical coordinator. So about myself, I've been at Netcetera for the past 1.5 years. I'm involved in most of the AI projects going in the company. And before I arrived here, I've been developing software and web. I've been working with web technologies for the past 9 years. So to give you a quick overview of what I'm going to go through. So first we are going to talk about how the private health insurance sector works in the Emirates. We are going to talk about Shafafia, which is the ontology that the Emirates are using for their medical claims. And then we are going to move on to how to tackle the problem using machine learning, and finish with the software integration and what we can do in the future to improve the systems themselves. So about the private health insurance, most of you should know how it works. You go to a provider, you sign up for a premium somewhere, you pay them some sum of money every month, and they tell you that they'll cover every medical expense that you do at private hospitals. So in the system itself, there are 3 main entities, which are the member, that's actually yourself, the hospital that's providing the care for you, and the company that's providing the money for the treatment itself. The problem here is when the patient goes to a hospital, he makes a claim on the money that he has paid for the treatment at his insurance provider, and then his insurance provider needs to decide whether they'll pay out the sum or not. The issue here is that these medical claims can get tweaked by the hospital, and they can add some, let's say you have a headache and then they prescribe you X-ray treatment, MRI scan for your brain, they give you some pills, and instead of spending like $5 for the treatment, you spend $50. And that's defrauding the provider that's giving you the insurance policy. So this is the problem that we are targeting in our work. We need to make a system that will find these anomalies, and in the first version of the project, we target upcoding as a type of fraud, which is basically adding more activities or procedures to the claim itself. The current systems that exist in the sector are only rule-based. That means there's a guy somewhere who's doing some continuous management on them, and is creating business-specific rules that are only valid for his area. The issue is that the doctors, for example, can learn these rules and choose to go around them. So if it bypasses the rule system, there is nothing the company can do to detect the fraud, except manually auditing every single claim, which in some cases it's completely impossible. So first, in order to have to be able to extract some data from the medical claims, they need to be digitalized, of course. In order to do this, most of the countries worldwide have adopted this system of electronic health records, which means every single encounter of the patient with the hospital exists as an information in a computer system. This allows us to leverage the information in order to improve the care that they are providing. So as I said, it's widespread. Most of the countries already adopt it. And our challenge is to unlock the information that's hidden in these electronic health records. Understanding what's hidden there can help us fight the waste, abuse, and fraud, and help with lowering down the cost that we are paying for the insurance policies. So the Shafafia is the standard that Dubai and Abu Dhabi have already implemented in their, their health system. So it's a system for exchange of electronic transactions. It has very specific business rules, and every single insurance provider and hospital has to follow this system in order to get paid by the country. It defines the key standards on how this information is exchanged in the system itself. So it consists of a person, who is the guy actually buying the insurance policy, a payer, who is the company that's giving the insurance policy, and a provider, which is the hospital giving the care. Sorry. Between the payer and the provider, there is a claim that's being exchanged, and this claim is the electronic health record, which contains the information about the treatment. Between the person and the provider, there is an encounter, which means every time you go to the hospital, an encounter happens. And this encounter contains the information about what kind of prescription you were given, what kind of diagnosis was found in your case. And for this type of encounters, every time a single claim is made. This claim is basically an invoice that's asking the provider to pay a certain amount of money. And as a return statement, the payer issues a remittance advice. And that's the fallback information that says, hey, we are going to pay you only this, this, and this. So to give you a quick overview about the data that we have received, we are working with a medium-sized insurance company currently in Dubai. We received data for 2016 and 2017 from them, which contains about 368,000 claims, which are made by 1,567 medical providers. There are about 1 million activities. Each activity is encoded with a CPT code. This is a standardized ontology that they are using in their system. There are about 10,000 distinct clinicians in the system, with 12,000 diagnoses encoded with ICD-10 ontology. This is the one that the entire world is using. Out of those, 35% are primary diagnoses. So a primary diagnosis happens when the clinician, that's the diagnosis that the clinician gives when you go to him for the first time. And after that treatment, you can get diagnosed with secondary diagnosis. And the total net sum is 160 millions approximately. This is in dirhams, which is the national currency of the Emirates. You can divide it by 4 in order to get the sum in euros, in order to understand how big this problem is. We are expecting that about 10% of this sum is subject to fraud, waste, or abuse. And using the rule-based systems, these companies can only achieve a denial rate of about 5%. This is not enough for them, as they are expecting the whole fraud, the size of the whole fraud that's happening in the system to be around 10%. So our job is to make a system that will increase this denial rate from 5% to whatever we can achieve. Of course, the goal being set near about 10%. Machine learning comes, of course, hand in here, because it doesn't have to follow the rule-based systems, which, as I said previously, require some continuous management and expert knowledge. And machine learning helps because we can quantify this information that's available on the claims and compare it against the history. And apart from this, machine learning models can adapt to new patterns that the clinicians are devising, because, of course, they can learn about these rule-based systems and just ignore them. And as final thing, they can learn from the judgments of the auditors that are manually investigating these claims. So in order to represent the problem that we are tackling, we can use a multigraph representation, where each node is an entity from the healthcare system. It could be a member, a claim, an activity, a diagnosis, a provider. And we can define an edge between them, which means which indicates its relationship between the entities. For example, we can have a clinician and a member, and those two can collude. And for example, this member goes to the hospital every single week and just does treatments that defraud the health insurance policy. And for that, he gets some kind of reward. So it's an iterative process of knowledge discovery, and here we use data analysis and visualizations to see what's happening inside the system. So the first topic that we actually try to fight against is the claim-based fraud. So we are trying to find on transaction level. We need to indicate which claims are the anomalies and which claims are the normal ones that should be paid. But the problem here is that the anomalies in the system are not necessarily fraud, because you can have some treatments that really cost a lot of money because they are, for example, healing some very rare medical diagnosis, and there's no way we can figure that out before we have any expert knowledge on healthcare. So apart from that, the only way to quantify the amount of fraud, because the health insurance companies are paying on transaction, is only through the claims. For example, if we are about to talk about the clinicians and we found out that this clinician is doing some fraud, there's no way we can know how much fraud he made in the time frame that he has been working for the hospital. So of course, before we start talking about machine learning, we need a way to represent the clinicians using numeric vectors. This is the key component in our modeling process, and it's very challenging because the set of the values that the claim can take are a lot, and the claim doesn't necessarily have all the information in it, so it's very sparse. And if we try to do some manual feature selection, this is impossible without being an expert in the field. And apart from that, of course, the vectoric representation should capture the semantic meaning of the claim. So we tested and evaluated 3 approaches. From natural language processing terminology, the first one is based on bag of words. The second one is based on some manual descriptive features that we have defined. And the third one is vector representations using medical embeddings, and this is a current research topic that we are working with Georgi. So, the bag of words representation, if you've been doing some research in natural language processing, you'll know about it. It's a simplified n-gram representation. It's also sparse, which describes the claim itself as a concatenated vector of term frequencies of the activities and diagnoses that are present there. It's very computationally expensive because of it, and requires a lot of RAM memory in order to process all the data inside the memory itself. One way to go around this problem is to reduce the vocabulary, which is what we did. For example, every activity or diagnosis that in the whole data aggregated appears more than 5 times, we have completely removed it from the vector. In the end, this is what we are left with. So we have claim 1, claim 2, and claim n, and as rows, and the columns represent the activities, which are the CPT codes, and the diagnoses, which are the ICD-10 codes. And of course, the values are the amount of times this certain activity has appeared on the claim itself. After that, we wanted to use some of the knowledge that we obtained during this process with the medical claims, and created some manual features which are trying to describe the claim as best as possible. This means that we are counting the number of secondary diagnoses, because usually when the clinicians try to make something dirty, they are usually adding more and more activities to the more and more diagnoses to the claim itself. And apart from that, we wanted to capture the price fluctuations inside the claim. So that's why we use the descriptive statistics, meaning we took the maximum, minimum, standard deviations, sums, medians, and averages of the net prices of the activities that are on the claim, their quantities, the frequencies of the activities per type, which means there are multiple types per activity. They could be drugs or pills. They could be some kind of procedures like brain scans or something, and so on. We also took the frequencies, so how many times a certain activity appears on 1,000 activities, and the probabilities of these occurrences, which are computed as a complex probabilities from the entire claim base that we have. And using the intuition, we thought that this method would take the claims that have high price fluctuations. For example, they have many cheap activities and one that's very high priced, and that should raise the alarm. Some frequency deviations, meaning they prescribe some very rare activities that are very expensive, and just overall some unusual prescriptions. So using these matrices that we defined before, now we can tackle the problem, and our goal is to detect the top abnormal 10% of claims. For this, we use an approach based on isolation forests, which are based on decision trees. So basically, every point that requires the least amount of partitions inside the data is considered an outlier according to this algorithm. And the output of these unsupervised anomaly detection models is actually just fed into the supervised pipeline, because at this point of time, before this, we didn't have the remittance data, so we didn't know the answer that the insurance company has sent to the hospitals. And we tried to tackle the problem as a supervised problem, but I'll talk about that later. Another thing that we tried to solve the issue with the sparsity of the bag of words approach is to use the autoencoders, which are basically two neural networks. One acts as an encoder of the data and one is a decoder. What we want to do is detect anomalies using this approach, and we do this by minimizing the reconstruction error that happens inside this network. So the encoder takes the input data, generates some kind of embedding. This embedding is then fed into the decoder, and the goal is to reconstruct the input that was fed into the encoder at the beginning. So here we describe the architecture that we used for tackling this issue. So we use a neural network with 4 layers. The first 2 are the encoder. The second 2 are the second 2 layers are for the decoder. We use L1 regularization during training and batch normalization and 50% dropout in order to avoid overfitting. As I said previously, the cost function here is minimizing the reconstruction error that happens inside the network. And here are the results that we have obtained. We can see from the curve that the model converges nicely. However, in the second picture, you can see that the anomalies themselves are not distinctly separated from the real data. So at this point, we realized that this problem cannot be only tackled in an unsupervised way, so we have to do some supervised models. And based on the remittance data, we were actually able to do that. So the remittance data itself holds some information whether the claim was, of course, fully paid or not. Some of these claims have been manually audited because every single insurance company has a division inside the firm that works on going over a certain number of claims, as many as they can handle, and try to detect fraud, waste, or abuse inside them. And using this information, we can build a supervised classificator. So we define the problem as a binary classification issue, which means we assign a positive class to the claims themselves if they're found as fraudulent. Not necessarily, because there are denial codes, which maybe a claim wasn't paid in full of some error that was made at the hospital during the process. But that doesn't matter much. So we say that a claim is positive only if it had a single activity that was denied on it, using a denial code that's related to the problem we are solving, and that's upcoding. And if all the activities have been paid into the claim, we say that the claim is a negative, or that the claim is completely fine. So we took the data, and we found out that we have about 80. We found out that we have 80,000 positive claims and about 350,000 negative instances. So we are dealing with a highly unbalanced dataset here. So the client sent us an XMLs. This is the standard that Shafafia defines. So they have a bunch of XML files that they gave us. So the first issue was ingesting the data into a relational database, so we can somehow query it, figure out what's going on with the data itself before we can move on to the feature extraction step, which means based on the approaches I told about you earlier, the bag of force representation and the manual features, we were able to build 2 models based on this, of course after labeling the data. So in the end, in order to tackle the unbalanced issue, we built multiple models based on XGBoost, which are gradient boosted trees. And we subsample the data every single time that we build these classificators. And then we connect them into one ensemble model, which gives the prediction whether the claim was found to be fraud or not. After that, these claims that have been tagged positively go through an anomaly detection pipeline. We match those who were tagged as fraud and as anomalies, and then the final output is given as a combination of these two. These are the results that we have obtained from these approaches. So we are using the area under the precision recall curve as a metric because we are dealing with an unbalanced problem. And what we are interested in is maximizing the area that's below this curve. So the recall indicates how much of the fraud we capture, but if we catch as much fraud as possible, we lose the precision on the model, which indicates whether there are a lot of false positives inside the system itself. So here is how this curve was generated. We have some probability thresholds here that indicate the probability threshold of the claim being fraud or not. This means that if the threshold is set to 0.9, we catch 40% of the fraud, approximately, with a precision of 0.94. That means in 94% of the cases, we are very sure that 40% of the fraud was caught. So based on this, we defined 3 fraud levels, which indicate whether the claim was with a low score. That means it could be fraud, it could be not, but we let it pass because the precision here is very low. We indicate a middle. We get a middle class here. We say that this class, the claims that belong to this class should be manually audited by the company itself, because, as I said previously, that they have a division that's working only on this. And basically here we reduce the amount of claims that they need to process every month. So, and this clause here is the one that's automatically denied by the payment, by the system itself. You can see some general statistics that they're about the distributions of these classes. So in the low class we have about 30,000 claims. In the medium class we have about 15,000 claims. And in the low class we have about 5,000 or something. The point here is that by defining these rules, we basically lower the scope that the auditors have to, the auditors themselves have to go through every month. So we can point them in the right direction and tell them that, hey, here are some very suspicious claims that you should check, and don't waste your time checking everything else because it probably won't give you any significant results. So apart from this, the client required for us to build some knowledge discovery models. This means currently the model itself is a black box, and we have no reasonable explanation on how it's gotten its result, because we are dealing with an ensemble model that has thousands and thousands of decision trees. So the way we tackle this issue is by generating a local model. For example, on this picture, if we try to explain this instance right here, we built a local linear classifier around it. So we only use the points that are in its vicinity. So the nearest points near this, the point that we are trying to explain. We built a linear regression model around it. And we use the coefficients that we obtained for the features in order to generate an intuitive explanation. In the end, we get as an output something that looks like this. We get a percentage of how sure we are that the claim is fraudulent or not. In this section right here, we get information which features contributed to the claim being non-fraudulent and fraudulent. And on the right here are the actual values from the vector that was sent into this model. So after this, we focused on finding fraud by focusing on the clinicians. We use the aggregated data from the claims in order to get a representation for the clinicians. We are not considering the clinicians who have made a low amount of claims, because there are usually some noise that's in the data. And we've built multiple representations. Some were based on using activities that had no drugs on them. Some were based on using secondary diagnosis. Some were only using the primary diagnosis, and so on. But I'll talk more in details in the slides themselves. So we conducted 3 types of analysis here, which are univariate, bivariate, and multivariate analysis. In the univariate analysis, we tried to answer these 2 questions, which are basically how many times a clinician prescribed a particular activity in comparison with other similar clinicians, and how much a clinician has earned from prescribing a particular activity in comparison with the similar clinicians. In theory, this should be a visual model that looks something like this. So for example, for every single activity, we plot the amount of times that each clinician has prescribed. So in this box plot here, we can see how many times each clinician has prescribed this activity. This is the CPT code of this activity here. So we can see that there are a lot of outliers here, but one is clearly distinct. And the idea was to visualize this somehow on a software. So whenever auditor expects that a certain activity is often being used as a fraudulent activity, he can just go to the UI, check this box plot, and see which clinician was this one. So after that, we started with the bivariate models. And I took all the data and just, for example, in this case here, I used the sum price of the claims and the number of claims per clinician in order to describe the clinician with 2 variables only. And this is what I've gotten. And to me, this doesn't say anything. There are a lot of points on the graph itself, and we can get no reasoning, no inference from this. But what if there was a group inside this data where this linear fit would make sense? So for example, these dots here could be some specialists that are getting very low amount of claims, but they're very expensive because they're only healing large, very rare medical conditions. Or maybe this group here, this could be the general practitioners, which are only healing some common diseases, so the linear fit would be okay for them. Or these clinicians here. So the rational approach to solving this problem was to somehow cluster the clinicians into several groups. There are 2 ways to do this in our work. The first one was based on the data itself. So we built some data-driven models in order to see how the algorithms themselves will group these clinicians, and using the expert knowledge that we have. And that's by just getting the specialty of the clinician that he has graduated with and using it to feed the data, to enrich our data. So in order to tackle the data-driven clustering, we use 3 kind of representations, which are based on the term frequencies of diagnosis. So which clinician is represented as a vector of term frequencies of diagnosis. The second one is by using the the term frequencies of the activities only. And the third one is by using the diagnosis and the activities themselves. We also tried the inverse term frequencies, but we didn't get any good results. Here the visualizations using dimensionality reduction. We use TSNE, which is basically a model which maps the data from n dimensions to the amount of dimensions that we want, by trying to keep the distance between the points as it was in the high dimensional space. So using a data-driven approach, we were getting this one big cluster that we were not able to somehow split it up. And this is mostly because some of the diagnoses can be cross-specialty, can be prescribed cross-specialty. For example, any doctor can tell what you should do with a headache. And these are common activities that exist in the system. So in the end, we decided that we are going to use the expert knowledge that we had, and we obtained each specialty for each clinician, and that way we were able to split the clinicians into several groups. So we wanted to redo these bivariate models and see, based on the groups, how they will perform this time. So we analyzed the relationships between the net price against the amount of prescribed activities. So we take the price of the claims, of all the claims for a clinician, and all the prescribed activities that were on it, and plot them on a graph, and then do a linear fit on it. The second one is the net price against the amount of claims, and the third one is the number of activities versus the quantity of the activities themselves. In order to find the anomalies here, we use a modified z-score metric, and each of these linear models, as I said, is defined per cluster. I should tell you that these models are only used as decision support, which means they're not making the decisions themselves, but they're just helping the univariate models and the other models in order to get a complete score at the end. So after doing the graphs based on the peer groups, you can see that they're much better now. We can quite clearly see some of the outliers that are available in each peer group, and compare that against what we had previously. So for each clinician in this step, we generated a z-score, meaning indicating whether that given clinician for this type of model was found as anomaly or not. Here is another example. If we plot the probability plot for the distances that are available here, we can quite clearly see how many outliers we can detect in this with this method. So after this, we focused on multivariate analysis, and again, we used the bag-of-words representation by representing the clinician as a vector of term frequencies. I forgot to mention previously that there is no dependency between the activities and diagnosis in the terms of space. So it doesn't matter whether a certain activity was found to be before or after a certain diagnosis. So this is why the bag-of-words approach is quite successful in our case. So we cleaned all the clinicians with a low amount of claims, as they don't carry enough information in order to be evaluated. And we defined two different isolation forest scores. The first one is global, based on the entire population so we compare the clinician against its entire population. And another one which is per cluster, meaning we try to find the anomalies that are within the cluster itself. And another one is based on the cluster distance for the clinician to its peer cluster, is based on Mahalanobis distance, which is a distance measure between the point and the centroid of the cluster. And the distance itself represents the level of abnormality of the clinician. So we faced an issue with memory actually here. So in the pipeline, we first had to do some dimensionality reduction. We used SVD. After that, in order to remove some of the features that were not carrying information, we used variance thresholding, meaning we removed all the features with high variance. We measured these distances, and we report a single score as anomaly measure. And we do this process over and on, and we go to the client with the results. We have a discussion with them. We present a couple of clinicians that we think got caught by our system. And these are some of the responses that we received from them. So basically, you can see that, for example, we figured out that there was a pediatric consulting adults and billing specialist fees. That means he inflated every single one of his claims by a high margin, if he should maybe by 100% or more. There were some cases like overbilling of CPTs, over-investigations, unrelated labs. I have no idea what these terms mean. GPs billing for specialists again, no consultations, also. And out of the 25 cases that we presented to them, they found a very high number of actual fraud in there. So in numbers, we analyzed all 2016 and 2017 claims, and out of those we flagged about 3,700,000 as most suspicious. The total value of these claims were over 21 million dirhams. They were made by 4,000 different clinicians, and 27 of these clinicians that the company themselves scored as most suspicious made a total of 5,000 claims. Apart from this, we've been working on a new system based on medical embeddings. Here we try to model the activities and diagnosis with some numeric representations. This is a novelty topic that me and Georgi are working on at the moment, and we are trying to approach the problem from a word embedding perspective. So if you heard about word embeddings, you should know about GLOVE. GLOVE is using the co-occurrence matrices of the words in the corpus in order to find the probabilistic relations between the words and generate some vector embedding based on that. We are trying to tackle the problem the same way. We use the diagnosis and activities. We put them in a co-occurrence matrix, and we generate some embeddings based on that. Now, using these embeddings, we can tackle the issue of waste, abuse, and fraud again by finding the intercluster distances between the activities and the diagnoses that are present in the claim, but this presentation will probably be for another meetup. So we do this analysis, and we do it by hand. So every time we get new data, every time we have to add something, I have to do it by hand, and this can be done every single time that the client requests. So we needed to somehow deploy the whole solution somewhere in software. We needed to do a real-time detection. So basically the client can send us claims in real time, and at the end of each quarter or each year, they can send us a batch of claims, and we need to process them somehow through the software. This is the architecture that we've come up with, but I'll get back to that later. Here's a simplified one. There is a server part, which actually has a claim processor. This is the part that that accepts the claim from the insurance company. It holds some scores that we generate about those claims. It has a web application that so the client sends us through an API. Sends data to the API, and it has a reporting system that works with these batches of data and generates reports based on the anomalies that we find in the data. And the kernel is the part that processes these claims and does all the machine learning stuff. So there is a web interface that receives the data from the server. So after the server accepts, they resend them back to the kernel. There is a message broker here that basically connects every single part of this system, because we have a training system that's used for generating new models on the fly. So during runtime, if I get new data, I can generate new models inside this part, and then I have to inform this model runtime system that a new model has been generated, and all of this is done through the broker. And there is, of course, some storage that we use for some historical data that we generate there. So going back to the previous picture, here's the server part. This is the one that sends the medical claims. Here's the web application. The web application just accepts all the claims and reroutes them to the message broker. The message broker is the one that sends an event that a request has been sent for scoring some data, and then there is this model process which basically listens for open tasks on the message broker, accepts the request, and sends it to the appropriate worker in order to score it in real time. There is a file system also in the middle here, which contains binary models. So each time we create a new model, we have to save it somewhere. So we serialize it and put it on the file system, and then during the initialization of this application, it just loads as many as possible. Because we want to be able to handle as many parallel requests from the client as possible, but we have limited resources, and these models can reach, basically because we are using gradient boosted trees, they can be very large in size. So we have a limited amount of memory here, and we have to somehow limit and distributely scale this runtime system on multiple servers. And there is this training system, which basically has an orchestrator, which gets the data from the broker and says, whenever I get some kind of request, just reroute it to the appropriate handler and create me a new model based on the data that you saved on the file system. So the problem that we are facing currently is that so far we were only working with a medium-sized company in the Middle East, and then our sales guy comes to us and says, hey guys, next month you're getting 12 million claims. So we were working with 500,000 claims only, and now we have to work with 12 million. I'm like, okay. So this architecture here will simply not do it, because this part here will cost probably millions, and it's something that we can't afford at the moment, I hope. So we have to use new technology, and based on the industry standards that are defined for big data at the moment, we are planning to switch from a relational database to using Hadoop or the HDFS system that they offer, which can be distributedly scaled on multiple servers. For the stream processing part, instead of using the web API, we'll plan to use Apache Spark as a stream processor and do all the algorithms and anomaly detections that we do on the stream processor itself. And then basically, instead of using message broker, we are going to switch to Apache Kafka, which seems to be the industry standard at the moment. So to conclude this was a journey that lasted for about 3 years in Netcetera. We were able to basically build a product without having any prior knowledge in the first years. And by building this product, we learned a lot about building machine learning software that's supposed to go on production and be used by actual people or auditors, and somehow help them achieve some of their tasks much easier and lower actually the premiums of the healthcare insurance policy in the Middle East. Thank you, everyone.
Thank you, Aleksandar. Stay there. Stay. Huh? You're answering questions. So feel free to ask questions if you have now, and I will ask the guys that are watching this online to also ask questions, but I will ask them in their name. So, do you have any questions? Okay, while you are thinking,
yes.
Thank you first of all for the nice talk. I'm interested for this project to work successfully. Actually, you needed a lot of knowledge expert knowledge, right, from the doctors there. So did you go there and, I don't know, visited how they make the claims and stuff like that? So can you comment?
Yeah, so just to repeat for the stream, we are asked whether we needed some expert knowledge from the client itself. Yes, we were able to go to Dubai twice, and we actually had quite lengthy discussions with the client that described their process of auditing the claims themselves and how we should actually approach and solve the issue from their point of view.
2 times was enough?
Yeah. According to the results, yeah. Yeah, of course, and email transactions all the time. Anyone else?
Okay, let's go with a question from the live stream. Okay, do you have any specific way of deploying models to Android, I guess, to mobile platforms, and do you use any service for it? Where do you run it?
No, we are not.
Repeat the question.
Okay, so the question is whether we are deploying any models on mobile-based systems. No, currently not. We are deploying everything on a server that's specifically made for that's running this application that I explained previously, and then we are just abusing it as a web service.
I can mention here that for the NCA phases, we wanted to run the model on iOS, on mobile phone, but there we had trouble running the TensorFlow within the mobile phone. There is the machine learning ML kit or something as well, but it's not compatible with what we had. But our idea, at least for the NCA phases, was that we can build the model, deploy it on the mobile phone, and run everything offline.
That's great.
Yes.
Please.
When your model detects that claim is fraudulent, is there a way to say also why it's fraudulent?
Yeah. That's what the question is, whether we are able to tell why a claim was marked as a fraudulent or not. So the answer to this question was actually in the presentation when I talked about the knowledge discovery. Yes, we have a system for that basically just builds a linear model around this claim, uses the nearest claims that we found the data around it, built a linear regression model for those data points only, use the coefficients as some kind of weights for the features, and then try to build an intuitive explanation based on that.
Do you give it as a result beside the classifier?
The question is whether it's given as a result. Yes, this is available on the web application. So the client can send a request saying, "I will tell me why claim ID something was defined as fraud," and we give them back the response as an object.
Okay, first, congratulations on the great talk, explained in detail. My question is, are you satisfied with the results that you're getting from the classifier, comparing to, let's say, an educated guess from an expert with the knowledge?
So the question is whether we are satisfied with the results and whether it's comparable to an expert or not. I can't say currently, because from the claim analysis, we haven't been able to discuss the results with the team that's available on the other side in Dubai. But according to the analysis that we did for the clinicians, they were quite happy with the results. And that's the point at which we sold actually the product. So I would say yes.
About the natural language processing, do you work with Arabic language or
The question is whether the claims are in Arabic language. No, they're using the standard. So we are not doing any natural language processing here, but we are using methodologies that are tackling natural language processing issues in order to solve this problem here, because the claim itself can be represented as a corpus of activities and diagnoses. In natural language terms, that means that the activities and diagnoses are words, and the whole claim is just a document.
And here we use codes, so every activity and every diagnosis is just a code, and we use codes as words. So there is no language, it's just
Do you use the ICD-10 code?
Yes.
Yes.
They have ICD-9 and 10, and there I think we had some troubles with that. But basically they want to use ICD-10 for all the future things they have.
I wasn't present at the lecture, excuse me, but do you use DRGs?
No. I forgot to mention that we are only tackling the issue of finding fraud in outpatient claims. So for inpatient claims, they are only using the DRGs, and that's basically controlled by the ministry, so we have no connections there.
One more question from the stream. Any plans on using PyTorch? Have you ever tried something?
No, currently not. We are only the autoencoder was built using TensorFlow, so we plan to go in that direction.
Do we have more questions? Or we can call it a day. Let me just check one more time. So no more questions from the stream. If we don't have any more questions here, I would say that we can continue chatting after the end of this event. I would like to thank you all for coming on this day. They told us this is the second time that we organized a data science meetup on name day in Macedonia. Last one was on Mitrovden, this one is on so we don't like to keep you all from the Sarno or whatever is there.
What is the next one?
I don't know, it's the next one. Thank you all for coming. Again, great thanks to Netcetera, Aleksandar, thank you very much. Krisitjan, thank you very much. And then see you next year.